So welcome to the second part of this tutorial. So we've just been through the cake cutting part. So what we're going to talk about now is we're going to talk fairly briefly about dividing divisible homogeneous goods. This is a super special case of cake cutting. We're going to focus on some things that we can do more easily in this setting. Then we're going to move on and mostly talk about indivisible goods with a small focus on some indivisible bads as well. And then depending on how we go for time, we have some more topics which we can explore. Okay, so let's get going and talk about divisible goods. So what do I mean by this? What I mean is, once again, we're going to have n agents, 1 through n. We're now going to have, instead of a cake, we're going to have a set of divisible goods m, which we'll call G1 through Gm. Okay, again, we're going to have allocations, and allocations will just be partitions of this set of goods. And allocations are going to be written as vectors here. So AI, the allocation of agent I, is an m-length vector denoting what fraction of each good agent I receives. We have these feasibility constraints. The first one says that no agent can be allocated less than a 0 fraction or more than a 1 fraction of each good. And the bottom one says that the total allocation of each good must be at most 1. Right? It could be a partial allocation or complete, but we can't allocate a good more than completely. And just in this divisible goods part, we're going to keep assuming additive valuations. Okay, so your valuation for a bundle is just the sum of your valuations for each part of that bundle. Okay, and as I said, this is a special case of cake cutting, even a more special case than anything we saw before, because the valuation functions can now be described as something like this. So these look kind of like those piecewise constant functions from before, except that now the breakpoints are actually known. Right? The first third here is G1, then G2, then G3. We're not necessarily going to assume normalization though, so in that sense it's perhaps slightly more general. Okay, so let's start with a super easy case, which is the case of n equals 2. And there's a pretty well-known procedure called the adjusted Windup procedure. Nisag mentioned this a little earlier. It's by Brahms and Taylor from 1996. And what it does, it takes as input, here we will require our valuation functions to be normalized. And what it's going to do is order the goods by the ratio of how much agent 1 likes them to how much agent 2 likes them. So here's a pre-processed valuation table. Instead of those valuation functions that we saw in the first half, now our valuation functions are going to be able to be expressed in a table like this. Okay, so the examples are going to look like this now. We see on the left we have a good that agent 1 really likes relative to agent 2, and on the right the opposite. So what the procedure does is it's going to divide the goods so that agent 1 receives, there's going to be some breakpoint where to the left of that point agent 1 receives all the goods, and to the right of that point agent 2 receives all the goods. Okay? And the objective here is going to be to divide these goods so that each agent receives exactly the same utility. Right, so in particular, this might require that a single good is divided between the agents, but at most 1. So if we run that on this example, what you get is that agent 1 is going to get goods 1 and good 2, agent 2 is going to get goods 4, 5, and 6, and then to impose this equitability criterion, we're going to split G3 50-50, and you can check that each agent gets a valuation of a utility of 65 there. Okay, so that's the adjusted Windup procedure. And it's fairly easy to see that this is MV-free and therefore proportional, it's equitable, and it's Pareto optimal. So just to remind you what these terms mean, or if you weren't here for the first half, MV-free means that no agent would prefer to receive the bundle of goods that another agent gets. Proportional means that each agent should get 1 over n fraction of their utility for the entire bundle of goods. Equitable means that each agent gets the same utility, and Pareto optimal means that we can't make anyone better off without making someone worse off. The equitability here is by definition of the procedure. Proportionality is easy because it's impossible to give each agent less than half because of the way we ordered the goods. And we know that for n equals 2, proportionality actually implies MV freeness. And Pareto optimality again follows because of the way we ordered these goods. Okay. So this is nice for n equals 2. You might want to extend it beyond n equals 2. Unfortunately, we can't. Right? Because as we saw in cake cutting, envy, freeness, equitability, and Pareto optimality together are impossible. You might hope that they're possible in this very restricted setting, right? Some things do become possible. This isn't one of them. So what about any two of these three properties? Well, envy, freeness plus equitability, this was our perfect partition from before, and in cake cutting we could get it, but it was hard. There was no kind of simple protocol that got this. But here, we can actually do it very easily. We simply divide each good equally among all the agents. Right now, everyone gets exactly the same bundle, and as long as valuations are normalized, they get an exactly 1/nth. So every agent gets 1/nth, and they all think that every other agent got 1/nth as well. What about EQ plus PO? Well, this actually stays impossible. There was a picture from the earlier slides, which when translated into this table form looks like this. Remember, Pareto optimality said we had to give good 2 to agent 3, so agent 3 got utility 1, and we had to divide this good amongst the other two agents. We couldn't give them both utility 1. Right, so that's still impossible. What about envy, freeness plus Pareto optimality? So this we could achieve with our competitive equilibrium from equal income solution. This is a special case of the cake cutting setting, so we can still do that. But actually it becomes quite a bit easier in this divisible goods setting. So we're going to focus on that just for a couple of minutes. Right, so what's our definition of CEEI here? Well, for one, we kind of saw before that our strong CEEI was really a better definition. So we're going to go with that now. And what it says here is that there's going to be some equilibrium price for each good. We're going to assume just for simplicity that every good is valued positively by at least one agent. This is just to avoid goods with price 0. And now what our competitive equilibrium condition says is that if an agent is allocated some non-zero fraction of a good, then that good must maximize their bang per buck, right? Their value to price ratio must be maximal for those goods. And our equal income condition says that the price of each agent's bundle should equal 1. All right, so this is exactly what we had before. And as Nisag told you earlier, the solutions of this kind of system maximize the product of the agent's utilities. In this setting, we can actually compute that according to this very nice convex program. So it's called the Eisenberg-Gale convex program. It was formulated way back in 1959. And what this does is it literally just maximizes the product of utilities, right? Or equivalently the sum of the logs, subject to the utilities of the agents being as we want them, and subject to the allocation being feasible. Right, and in this setting, it's been fairly recently shown that we can actually solve this convex program in strongly polynomial time. Okay, so when we have these divisible goods, we can compute our CEI allocation in strongly polynomial time. All right, so that's what I wanted to say about the competitive equilibrium from equal incomes. Let's move on to what we can say about strategy proofness. Now recall in the cake cutting setting, no deterministic mechanism could be both strategy proof and proportional. What can we do in this divisible goods setting? Well, first off, I'll just note that our competitive equilibrium solution is fair in the sense of envy-free, and it's efficient in the sense of Pareto optimal, but it's not strategy proof. And the reason that it's not strategy proof is because if there's some good that you like, but no one else likes, you might be charged some relatively high price for that good. You can reduce the price that you're charged for it by pretending that you like it a little bit less. And this might enable you to buy or be allocated other goods as well. All right, just to note that it is strategy proof in the large, meaning that if there are a lot of agents in the system, you can't benefit from misreporting your valuations. Okay, but this is not really usually what we want when we want to go for incentive properties. So what can we do if we want full strategy proofness in this setting? Well, not surprisingly, there are at least some impossibilities. In particular, one thing that we know is that you can't achieve better than a 1/m approximation to the optimal social welfare with any strategy proof mechanism. And by social welfare, I mean the sum of the agent's utilities. And this isn't too surprising, all right? As we kind of observed earlier, strategy proofness and social welfare are somewhat orthogonal to each other. Social welfare says you want to give it to the agent with highest valuation, but strategy proofness says you don't want to reward agents for just reporting a high number. But we're not going to be able to approximate social welfare, so we need to think about something else if we want to think about strategy proof mechanisms. So what Cole et al. Did in 2013 is they thought about approximating a different quantity. In particular, they thought about approximating the utility that each agent would receive under the CEEI allocation. And what they show is that they have a strategy proof mechanism that provides every agent with a 1 over E fraction of their CEEI utility. Okay? And how this mechanism works is there's kind of some underlying connections to the VCG protocol, if you know VCG. Basically what it does is it computes the CEEI allocation, and then depending on the externality that you impose on other agents, it basically burns some of your allocation. Right? So it's not a complete allocation, it's a partial allocation, which means that this statement can hold. It's an envy-free allocation, but it's not complete, it's not a full allocation, so it's actually not proportional. Yes, I believe so. I believe that the CEI utility is always at least the proportional utility. Yeah. Okay, so that's a nice guarantee. We might want to ask, can we get strategy proofness, envy freeness, and proportionality? Okay, and this can actually be guaranteed by the trivial mechanism that we've already seen. We can simply allocate everyone an equal fraction of each good. This is strategy proof because you can't change what you get, and it's proportional because you get exactly 1/nth of all the goods. It's envy-free because everyone gets that. Okay, so this is nice. It satisfies the properties, but it's not exactly, certainly not efficient. We wouldn't want to actually run this in practice. So what if we also want Pareto optimality? And perhaps not surprisingly, this is too much to ask. So it's been known for over 20 years that it's impossible to get strategy proofness, proportionality, and Pareto optimality at once. All right, so what you might want is something in the middle. You might want to get strategy proofness, proportionality, envy freeness, at least in some non-trivial way, right? With some benefits over and above this trivial allocation. And we've recently seen that you actually can do this. There's a mechanism, or a class of mechanisms actually, which achieves these three properties together non-trivially. So we don't get Pareto optimality, but we at least do get more than the trivial allocation. And additionally, what we get is we actually get a slightly stronger strategy proofness property. It says that not only can you not benefit from lying, but if you lie about your evaluations, you'll do strictly worse. And the way that we get that is we exploit a correspondence between these fair division mechanisms and a class of mechanisms called wagering mechanisms that are about eliciting probabilistic information. Right, so I'm not going to go into this in any more detail, but if you're familiar with things like proper scoring rules, like the Breyer score, we can utilize these in this fair division framework to get strict strategy proofness. Okay, so that's all I wanted to say about the divisible good setting, just highlighting some things we can do there that we can't do in the general cake cutting setting. So I'm happy to take any questions about that. Otherwise, I'll move on to indivisible goods. And that's where we're going to spend most of the time in this part. Okay, so indivisible goods model is very similar to the divisible good one, except that now our goods are indivisible, so we can't divide them. Again, an allocation will be a partition of some subset of the goods, where it's a strict subset if it's a partial allocation. Otherwise, it's a complete allocation. And each player is going to have these valuation functions which map subsets of goods to non-negative numbers. Okay, and now we're going to, at least at times, consider more general classes of valuation functions. Okay, so we still have our additive valuation functions. These are exactly what we've been considering so far, where a value for a good is independent of the other goods that you've received. We're also going to think about some more general classes. So we have submodularity, which says, I think the most helpful definition is the bottom one here. It says that if x is a subset of y, then the marginal value of adding an additional good to our X subset is at least as much as the value of adding that good to the Y subset. Right, so that's submodular evaluations. And an even more general class is subadditive. And that just says that the value for two subsets of goods separately must be at least as much as the value for those two subsets when you put them together. Okay, and both of these definitions are basically just trying to capture the idea, to different extents, of diminishing returns. Right? Generally, the more you have, the less valuable additional goods are to you. Right? It's still going to be the case that most of the results are going to be for additive valuations, and certainly unless stated otherwise, they're for additive valuations. All right, so one thing that's pretty obvious when we move to indivisible goods is that we need new guarantees. Right? The things that we've discussed before, MV freeness, proportionality, equitability, they simply aren't going to hold. So the classic example is if we have a single diamond that must be divided, allocated among some agents, say 3 of them, they all want this diamond, it's indivisible, only one of them can get it. Right? We're always going to have envy, we're never going to have equitability, and some agents aren't going to get their proportional share. Not only that, but we can't even multiplicatively approximate these things. Right? Some agents are going to get 0 utility, so it's not obvious what notion of approximation we can even use here. And most of the guarantees we discuss are going to have kind of an up to 1 good flavor. It's going to become very clear what I mean by that. So let's start with the first of these up to 1 good style guarantees that was defined, and the most popular one, which is called MV freeness up to 1 good. So what this says, here's the definition of MV freeness. There's some blanks here that I'll fill in. So that's MV freeness. MV freeness up to 1 good says that for all players I and J, there must exist a good G in J's allocation, such that when you remove G from the bundle that J receives, now agent I prefers their own bundle to J's bundle with good G removed. So in words it says, sure, agent I might envy agent J, but we can remove that envy by eliminating a single good from J's bundle. Just point out we have this, there exists a good G here, but sometimes AJ would be empty. We don't want to consider that a violation. So I could have defined this kind of in a more lengthy and more formal way to avoid that. All right, so that's EF1. The first question is, can we achieve allocations that satisfy EF1? So one classic way we can do this is by the round-robin algorithm. So how round-robin works is we fix an ordering of the agents, say agent 1, 2, 3, and then in rounds we let these agents pick an item, their most preferred remaining item in order. So agent 1 picks an item, then agent 2, then agent 3, then agent 1, and so on. Right? And it's pretty easy to see that this round-robin mechanism satisfies MV freeness up to 1 good. And here's a little animation showing how. Animation credit to Ariel Procatra again. So suppose we have these 7 items to allocate, and we're going to have 3 agents here, the green, the orange, and the red. So let's suppose that they pick in that order, green, then orange, then red. And maybe they choose in some order like this. Well, it's pretty easy to see that the green agent shouldn't envy anyone, right? They were first in the order. If you were first in the order, why would you envy someone who was second or third in the order, right? You don't want that what they want. You could have just picked it. You went before them. So the only people we have to worry about who might still have some envy are those further back in the order. So think about, say, the red agent who was last in the ordering. Well, sure, they might envy the other agents, but if we imagine taking away these 2 goods that were selected first, right, in essence, eliminating the first 2 rounds here, then we're left with this procedure that looks more like this, where we have these 2 are gone now. So now red is going first, followed by green, followed by orange, and then red, and then green again. Right? In essence, we've taken away 1 good from all the other agents who aren't the red agent, and we've created this situation where the red agent went first. Right? So by taking away 1 good from each agent, we've removed all the envy. Right. I'm going to give you one more algorithm for achieving MV freeness up to 1 good. It's not going to achieve any more properties over and above round robin, but it's going to be a nice algorithm that we'll come back to achieve other properties as well. Okay, and how this algorithm works is one at a time, we're going to take in, so we're going to start with none of the goods allocated. One at a time, we're going to allocate goods, or 1 good at a time, to a player that no one envies. Okay, so this will always be possible as long as you can think about an envy graph, right? Where we have agents I and j. We're going to draw an arrow from agent I to agent j if agent I envies agent j. So as long as this envy graph that we can draw is not cyclic, there'll always be some agent who's envied by no one. Okay, so we can always do that. If there is an envy cycle, then what we can do is we can simply rotate the bundles along that cycle and remove all the envy. And I'll show you an example of this in a second that I think will make it clear. Okay, and then the way this works is because we only ever allocate a good to an agent who no one envies, we can always remove the envy by just removing this most recently added good. Okay, so I'll run an example of this in a second. One thing that I want to note is that neither of these two algorithms I've just mentioned are Pareto optimal. They might be very far from it, actually. Okay, so let me just quickly run through how this algorithm would work. We have 3 agents, 6 goods, and here are the valuations. And here's the envy graph that we're going to construct. So suppose that we give good 1 to agent 1. This is a somewhat arbitrary choice. And now agent 2 and agent 3 both envy agent 1. So we'll draw these arrows. Then we have to give good 2 to someone who no one envies, either of these guys. Let's say we give good 2 to agent 2. Envy graph gets updated to look like that. Now agent 3 envies both of these players. We can give a good to agent 3. Some of these envy arrows will flip. Actually, now agent 1 envies agent 3, because agent 1 would rather have good 3 than good 1. All right, we can keep doing this. Eventually, we might get to a point where we have a cycle. So you can check here, actually, agent 1 would prefer agent 3's bundle to their own. Agent 3 would prefer agent 2's bundle to their own. And agent 2 would prefer agent 1's bundle. So how we deal with this is we rotate these bundles, which looks something like that. And by definition, this is going to remove all those envy arrows. All right, and we can proceed like that. Eventually, we'll arrive at an EF1 allocation. Okay, so we can get EF1. Just like in the last section, we're going to think about, can we get this in combination with other properties? So I guess I should point out here, this is particularly inefficient. One way you can see that is that we've given this good G4 to an agent who doesn't even have any value for it. Right? In any Pareto optimal allocation, good G4 should have gone to agent 2. So can we kind of remedy this? Turns out that we can. And to remedy it, we're going to look at an algorithm called the maximum Nash welfare. We've seen this already with Nash optimal solutions, the solutions which maximize the product of the agent utilities. In the indivisible setting, just happens that we call it max Nash welfare, or MNW. So this is the allocation that maximizes the geometric mean of the agent utilities. There is one kind of slight bug here with the indivisibilities. In the divisible world, the cake-cutting world, it's never going to be the case that an agent receives 0 utility. If an agent receives 0, we can always give them just a little bit more to get them off 0. This will always be best for the product. Like a 0 wipes out the entire product. This is as bad as you can get. With indivisibilities, it might be inevitable that some agents get 0 utility. Okay, so we need kind of a somewhat technical caveat to this definition. And that is that if it's impossible to give everyone more than 0 utility, what we want to do is first find an allocation that maximizes the number of agents who get non-zero utility, and then subject to that, maximize the geometric mean just of those agents. Okay, so with that said, let's think about what this allocation satisfies. And it turns out that it satisfies both envy freeness up to 1 good and Pareto optimality. Right, how can we see this? Well, Pareto optimality is easy to see. If you had a Pareto improving allocation, an allocation where everyone was better off without everyone was at least weakly better off and someone strictly better off, then this would have a higher geometric mean or more agents with non-zero utility. EF1, it's not so obvious. I'm not going to go through the proof, but it is pretty easy. What you can do is you can define this good GI star, which is the good from agent I's bundle that they value the most. And you can show that for all j, it's the case that if you remove this good GI star from agent I's bundle, then agent j will no longer envy agent I. That holds for all j. Okay, so just to show you what this does, it's not at all obvious that this is what this is the product maximizing allocation, but in particular it does give good G4 to the right person. Oh, okay, and I guess I should point out that it's EF1. There is some envy here. Agent A3 gets utility 5, but they actually envy agent A1, because if agent 3 received agent 1's bundle, they would get utility 2 plus 3 plus 1, which would be 6. But we can remove that envy by deleting this good here. Right? Now agent 3 no longer envies agent 1, because they would only get utility 1 plus 2, which is 3. Yep. Yeah, so you can definitely argue about it's a thought experiment. So you could definitely argue about whether this is indeed a satisfying guarantee to offer an agent, right? You say, okay, you might envy someone, but don't worry, if we remove the good from their bundle, you wouldn't envy them anymore. But we're not going to actually remove the good. We just think about removing the good. Does that answer your question? All right. So we can get these two properties together. The next natural question is, can we compute such an allocation? Right? And it turns out that the max Nash welfare allocation is actually strongly NP hard to compute, even when our valuation functions are additive. It's actually even worse than that, and we're going to come back to this a little later, but it's APX hard. So you can't get a p-task for it. Okay, so we can get EF1 plus PO, but we don't know how to compute that efficiently at this stage. One thing we can do is, if valuations are binary, then we can compute the MNW allocation in polynomial time. By binary valuations, I mean every agent has value 0 or 1 for every good. So this is a very restricted case. Actually, we don't even need the power of MNW here. Just Roundrobin will already guarantee us the two properties we want. But thinking about a more general case, it's been shown recently that there does exist a pseudo polynomial time algorithm for computing an EF1 plus PO allocation. So what this algorithm does is it uses a local search, so a sequence of item swaps and price rises, to compute an integral competitive equilibrium. So what an integral competitive equilibrium is it's a competitive equilibrium where no goods have to be allocated fractionally. Right, and the nice thing about the competitive equilibrium framework is that it guarantees Pareto optimality. This is a fundamental theorem from economics. The problem is that such an allocation might not, or such an equilibrium might not always exist. In particular, if you have equal incomes, which is what we had before, competitive equilibrium from equal incomes, that might not exist. Because if you have one good and you have two agents who want the good, if they both have the same amount of money, you can't decide who to give it to. You need one to be wealthier than the other. So what they do to get around this is they take unequal incomes, but they make sure that the equilibrium they get satisfies this property called price envy freeness up to one good. And what that means is it says that the price of agent I's bundle, in other words, the budget that we give agent I, is at least the price of agent K's bundle, take away a good. So it's the budget that we give agent K, take away one good from their bundle. And actually, this is a strictly stronger property than envy freeness up to one good. Right, so they guarantee this property, which guarantees EF1. All right, so you can kind of think of this EF1 plus PO story I've told in two ways. One way is good news. We can guarantee EF1 plus PO. That's great. Maybe we can search for stronger fairness guarantees. Can we do something better than EF1? And I'm going to get to that perspective in just a second. Kind of the bad news perspective is we have this pseudo polynomial time algorithm, but we still don't know whether we can get a polynomial time algorithm. So that's our first open problem for this part. Given that we still can't do this, can we maybe think about relaxing our fairness property to something that we can guarantee in polynomial time? So that's the direction that I'm going to go first. And I'm going to think about proportionality up to one good. Right? Proportionality was weaker than envy freeness. Proportionality up to one good is going to be weaker than envy freeness up to one good. So what this says is that for every agent I, there should exist a good G where when we add good G to agent I's bundle, agent I receives utility at least their proportional share. Right? This is the proportional share here. It's the value for the entire set of goods divided by n. Okay, so on an example like this, suppose we made this allocation. Well, agent 1 here is not receiving their proportional share. Their proportional share would be 3.5. That's the sum of their valuation for all the goods divided by the number of agents, which is 2. Okay, they're getting utility 1, that's not proportional. But if we added one good to their bundle, they would be receiving their proportional share. Okay, that's just this calculation here. We can add G2, now they get utility 4. This is strictly weaker than EF1, right? This allocation here does satisfy prop 1, but it does not satisfy EF1. Even if we take G2 away from agent 2's bundle, agent 1 still envies agent 2. Okay, so it's not EF1, but it is prop 1. And it turns out that this weakening is helpful from a computational perspective because we can actually satisfy prop 1 plus PO in strongly polynomial time. And the way that we can do this is construct a CEI allocation. A CEI allocation might be fractional, right? So it's not valid for our indivisible good setting. But if we round it carefully, we can guarantee prop 1 plus PO. And this is kind of interesting because we know that there exist instances where any such rounding technique will not give us EF1. Okay, so this seems like this is at least some kind of hard boundary between prop 1 and EF1. At least these techniques won't work for EF1 plus PO. All right, but overall good news on the computational front if we relax the fairness requirement. What about the other perspective where we want to think about existence, where we can already guarantee EF1 plus PO, we want to ramp up the fairness requirement? So one way to do that is to define this notion called MV freeness up to the least valued good instead of up to some good. All right, and here's kind of the motivation for this property. Consider this valuation, these valuations and this allocation. You can see that this is MV free up to one good. Right? Agent 1 does envy agent 2. They get utility 5 for their own bundle, but they would get utility 15 for agent 2's bundle. If we take away one good, in particular we take away good G1 from agent 2's bundle, we could remove all this envy. Right? So this allocation is envy free up to one good. But we might want it to be envy free up to no matter which good we remove from agent 2's bundle. Right? This allocation is still not really what we would think of as fair. We would probably want to give G2 to agent 1 so that the agents get utility 10 each, rather than just giving this agent 2 an extra epsilon. So that kind of motivates this definition. So an allocation is envy free up to the least valued good if for all players I and j, and this technical condition that says every good in j's bundle that I values positively, it should be the case that if we removed g from j's bundle, agent I no longer envies j. So we remove the envy by taking away any good we want. All right, so does there always exist an allocation that satisfies this property? To think about that, I want to first define an allocation rule called LexiMin. So what the LexiMin allocation does, it's like MaxMin, if you've heard of that. What it's going to do is first maximize the minimum utility that any agent receives. Then subject to that, it's going to maximize the second minimum utility. Subject to that, the third minimum, and so on. Right, so here's what it does on that example from earlier. Perhaps this is not too instructive. You see here the minimum utility is 5, second minimum is 6, third minimum is 11. There are other ways here that we could make the minimum utility 5, but none of them result in the second minimum utility being as high as 6. All right, so we can use this to satisfy EFX at least in some restricted cases. So Plout and Roughgarden showed in a Pseudo 2018 paper that if players have identical valuations, this holds for general valuations, by the way, not just additive, not even just subadditive. I think it can be completely general valuations. Then the LexiMin allocation satisfies EFX plus PO. What I mean by identical valuations is that all the rows in this valuation matrix are the same. Okay, they also showed that if you have just two players and they have normalized additive valuation functions, then the LexiMin allocation satisfies EFX plus PO. They don't have to be identical. These are, of course, some fairly restricted cases. And a big open problem that we have is, does there always exist a complete allocation satisfying EFX? People have thought about this for a few years now, and no one has a solution. All right, you may notice that I put this word complete in here. And that is because of a recent result where, well, I guess I should start by asking the question, what if we are allowed partial allocations? If we allow partial allocations, then it's easy to satisfy EFX. We can just throw all the goods away. Right, this is even completely envy-free, but it's a fairly useless allocation. What was shown recently by Karayanis et al. Is that there exists a partial allocation that satisfies EFX, so far that's nothing particularly special, but it also achieves a 2 approximation to the optimal Nash welfare. Right, so it both satisfies EFX, and despite being partial, it's still a good allocation, in some sense of good. They also show that no EFX allocation, even a complete allocation, can achieve any better approximation than this. Okay, so let me kind of wrap this part with the following slide, which just sums up what we know about existence and computation of these 4 properties with and without PO. So prop 1 is kind of easy enough that we can do everything we want. Freeness is hard enough that we can't. And for EFX, and to a lesser extent EF1, there's still plenty of questions that we don't know the answer to here. Yeah. No, computer LexiMin allocation is computationally hard. I'm not sure about in these special cases. These are more existence results than computational results. All right, so all these properties that I've talked about so far kind of fall in a nice hierarchy. You have envy-freeness, implies EFX, implies EF1, implies prop 1. Now I'm going to talk about a slightly different flavor of guarantee. It's kind of a pretty cool definition, but it feels very different to the ones we've discussed so far. It's called the MaximeinShare. And the idea of the MaximeinShare is that it's kind of a generalization of the idea from the cut and choose protocol. It says, if I partition the goods, all the goods, into n bundles, but then I receive an adversarially chosen bundle, how much utility can I guarantee myself? It's like, if I cut the cake and then someone else chooses, how much utility can I guarantee myself? Okay, so to formalize that, we can define this thing here, which is the MMS share of agent I when there are k agents in the system and our set of goods is S, and I am unfortunately going to need all of that notation. And that's just the max over possible partitionings, possible k partitionings of our set of items S, of the minimum value that I have for any of those bundles. Right, so this is just the math for this English statement here. And the MMS allocation is one where the value that I get from my allocation is at least the MMS share when I partition all of the goods into n bundles. Right, note that this share is strictly less than the proportionality guarantee, and that's because the very best I can do when I partition these goods is I can partition them perfectly evenly. Right, that's the best I could possibly hope for, and I get the worst of those bundles. That would be exactly my proportional share. Kind of in most cases that you can think of, when you partition them, there's going to be some inequality between the bundles, and you're going to get the worst one, so it's going to be less than your proportional share. Right, so let's just think about how we can compute this MaximeinShare, or how we can think about it. If you're agent 1 and you need to bundle these goods into, partition these goods into 3 bundles, you can put G1 and G2 in one bundle, that's the value of 3, G3 in its own bundle for 3, and the last 3 in their own bundle for 3. So your MaximeinShare is the minimum of 3, 3, 3, which is 3. If you're agent 2, you can do the same thing, but you can't equalize your utilities. You have a 10 bundle, you have a 5 bundle here, and you have a 5 bundle here. Your MaximeinShare is 5. If you're agent 3, we can do the same exercise. Your MaximeinShare is 4. Okay, so for quite a while, we didn't know whether this property could always be guaranteed or not. Then there was a breakthrough result in 2014 by Prakacha and Wang, who showed that there actually exist instances, and it's a very carefully crafted instance that they have, where no allocation satisfies MMS. Right? At least last I was aware, in all kind of real-world instances, it seems like you can always guarantee a MaximeinShare. So you need these very carefully crafted instances. So what this did is it motivated considering approximations. So there are two types of approximations that you could reasonably think of here. The first one is kind of a fairly standard multiplicative approximation. We want to find allocations which guarantee you at least a C fraction of your MaximeinShare for some C less than 1. The second type of approximation you might hope for is to guarantee you your MaximeinShare, where instead of dividing the goods into n bundles, you're going to divide the goods into k bundles for some k greater than n. So we're going to make you partition the goods into more than n bundles and still give you your worst one. So the second of these was introduced and somewhat solved by Budish in 2011, and he showed that there always exists an allocation that satisfies this guarantee for n plus 1. So when you divide into n plus 1 bundles and you get your worst. And the way he did this was with an approximate notion of competitive equilibrium. Okay, so that second guarantee, that's the best we can hope for. What about the first style, the multiplicative approximation? Well, there's been kind of a long chain of results on this since that original 2014 paper. So Prakacha and Wang showed in that same paper that a 2/3 MMS approximation always exists. They had an algorithm to compute it, but it didn't run in polytime. That was improved by Manatatis et al. In 2017 to show that they could compute a 2/3 minus epsilon approximation in polynomial time. Then it was shown that you can always guarantee actually a 3/4 MMS approximation and a polynomial time 3/4 minus epsilon. And most recently, in an unpublished manuscript, it's been shown that you can in polynomial time compute a 3/4 MMS approximation. Right, so in the end what you get is this, you can write up this table. So what I've been telling you about are the additive results. So we have this lower bound of 3/4. We still don't know anything more than a fairly trivial upper bound. This is from the original Prakacha-Wang paper. It's very close to 1. So an obvious open problem here, or set of open problems, is to close this gap. Well, all of these gaps. There's these results for submodular and subadditive valuations as well. And all of these results come from that Godsey et al. Paper. Yeah. It needs to compute the value. And at least one of these algorithms, perhaps the most recent one, somehow gets around that hurdle. I'm not exactly sure how. They somehow get this guarantee without computing the, without actually computing the MaximeinShare. Yeah, it's kind of a clever thing. But no, they're not given the MaximeinShare as input. They're just given the valuation functions. Yes.
So that's why this last paper does not actually compute the MaximeinShare.
Yeah.
It computes an allocation that satisfies 3/4 MMS without actually computing the MaximeinShare themselves. And the previous algorithms, I believe, compute external approximations of MaximeinShare values.
Okay. Right, so that's MaximeinShare. And it was actually, okay, so it was then observed by Baumann et al. In 2018 that actually sometimes you can do a lot better than the guarantee provided by the MaximeinShare. And they had kind of a nice example, a nice observation, which is that they want to guarantee the MaximeinShare ExPost. Right? And they want to guarantee it ExPost with respect to all possible groups of, like when you restrict the allocation that you have to all possible groups of players. Right? So maybe we allocate goods to a whole lot of players, but then I might be able to say, well, hold on, if we just restrict this allocation to my allocation and one other player's allocation, I want to get my MaximeinShare with respect to just the two of us as well. So let me kind of show you what I mean by that. Here's the example that Barman et al. Had. The MaximeinShare of agent 3 is 2 epsilon, right? And the way you can see that is think about how you can best bundle, how agent 3 can best bundle these goods into, or partition these goods into 3 bundles. They can put a 10 and a 0 together, another 10 and another 0 together, and then the 2 epsilons together in their own bundle. Right, and then if they receive an adversarially chosen bundle, they get a utility of 2 epsilon. Okay, so if we do something like this, this is guaranteeing agent 3 their MaximeinShare of 2 epsilon. But now here comes this ExPost condition. Ignore that math down the bottom. Here comes the ExPost condition. Let's say that we wipe out agent 2 and the goods that agent 2 received. Okay, so now we're considering the subinstance consisting of agent 1, agent 3, and the goods that were allocated to them. Now, with respect to this instance, agent 3 is not getting anywhere near her MaximeinShare. Because now, if she were to take these 4 remaining goods and partition them into 2 bundles, she could partition a 10 with an epsilon and a 10 with an epsilon, and her kind of ExPost MaximeinShare would be 10 plus epsilon. Instead, she's only getting 2 epsilon. Yeah, so that's the idea behind group-wise MMS. Okay, so allocation A satisfies group-wise MaximeinShare. Basically what that math says is if you cannot find an example or find a subinstance of the allocation like we just did. So what Barman et al. Show is, of course, this is a strictly stronger property than regular MMS. So it also can't be guaranteed, and also these kind of known bounds still apply. They do show that for additive valuations, you can guarantee at least a half GMMS allocation, meaning that you can always guarantee someone at least half this utility. Then they can find it in polynomial time. What the algorithm does, actually it looks very similar to that EF1 algorithm we had right at the start. What they do is they allocate the goods one at a time. They select a player who's not envied by anyone, and they allocate them, rather than just an arbitrary good, they do something a little smarter. They allocate them their most preferred unallocated good. So just doing that like slightly smarter thing suddenly gives you an algorithm which is pretty good. All right. I also want to point out that this is called group-wise MMS, but it's still really a guarantee on a single agent's utility, right? It doesn't really talk about utility guarantees we want to provide to groups of agents. Okay, so now we've talked a lot about MV freeness and proportionality and relaxations of them. That's what we've been talking about so far. Let me briefly talk about relaxed equitability notions. It's the third of the 3 properties we had for cake cutting, or the 3 main properties we had. So equitability suffers exactly the same problems as before with indivisibilities, right? Okay, so what we can do is we can relax it in exactly the same way we did for MV freeness. So we can define up to 1 good and up to any good variance. All right. What I want to do really is point out a couple of very interesting differences between these equitability variants and the MV freeness variants that we had before. So one interesting thing is that we can achieve EQX with a very simple algorithm. It's, again, similar to that EF1 algorithm we had before. We're just going to allocate the goods one at a time, and we're going to allocate to the lowest utility agent the unallocated good that she values the most. Right, and you can show, it's actually pretty easy to see, that this achieves EQX. This is interesting because you can contrast this with MV freeness, where EFX is still kind of impenetrable and we don't know whether it can be guaranteed at all. Okay, well, what about EQ1 or EQX in combination with Pareto optimality? Well, in this case, the EQ variant seems to be actually a little harder than the EF variant, because it turns out that an allocation satisfying EQ1 and PO may not actually exist. Again, contrast this to MV freeness, where we know that EF1 plus PO always exists. In particular, something like the max Nash welfare solution always gets it. Okay, and this example is very much like the cake cutting example that showed that EQ and PO couldn't exist. We have 3 goods that only agent 1 likes, and then 3 goods that both agent 2 and agent 3 like. Pareto optimality says that we must give all 3 of these to agent 1, and then we have to divide 3 goods amongst 2 agents. One of the agents must get only a single good, so this is inequitable up to 2 goods, not 1. Right? What we can show is that when valuations are strictly positive, so when you don't have these zeros, you can actually get EQX plus PO with the LexiMin allocation. All right, so moving on from equitability, now let's talk about group fairness. So now I kind of mentioned before that group-wise MMS was still a guarantee on individuals. Now we want to think about going beyond individual fairness. Right, so what guarantees can we provide to groups of agents? And here's kind of a toy example to tell you what I mean. So let me explain this picture. We have these 5 different types of players or agents. Circle agents care only about circle goods. Square agents care only about square goods, and these square/circle agents care about both equally. And if we're allocating 2 circle goods and 2 square goods, we might do something like this. And if you check, this is actually EF1. It's envy free up to 1 good. Like this, one of the square agents, they may envy these flexible agents, but only up to the removal of that 1 square good, because they don't care about the circle. So it is EF1. However, it seems to still be kind of unfair, because if we think about groups of agents, think about these 2 agents as being S and these 2 as being T, then our agents in S might think, okay, well, individually we don't envy these players in T, but if we, the 2 of us, could get all 4 of these goods, right, T's entire allocation, we could reallocate them amongst ourselves like this. The circle agent gets both circles, square agent gets both squares, and now they're both quite a lot better off. Like more than up to 1 good. They're now 2 goods better off each. Right, so in this sense, this feels like it's not even approximately fair to groups. So before I continue with approximate versions, let me define an exact version of what we want. And we call it group fairness. So this is going to be an exact version. It's not going to be satisfiable for indivisible goods. What it says in English is that for every non-empty subset S and T of agents, it should not be possible to redistribute the goods allocated to group T amongst group S in such a way that every member of group S is better off than they were under the original allocation, with utilities adjusted for group sizes. That's what this term is for. And that just says that, of course, if we take all the goods allocated to a big group and give them to a single agent, that single agent will be much better off. So we want to adjust for that. So that's group fairness. This generalizes lots of properties. It generalizes envy freeness, generalizes optimality, generalizes the core, generalizes all sorts of things that we can't get with indivisible goods. So we need some relaxations. And they're going to be of this up to 1 good style again. So there's 2 of them, an after and a before version. So what the after version says in black is basically what we had before. So it says it should not be possible to redistribute the groups allocated to group T amongst group S in such a way that every member of group S is better off, even when 1 good is removed from each of them. Okay, so we take our example from before. The way to see that this still fails, even this relaxed version, is when we reallocated group T's goods amongst group S, even if we take away 1 good from each agent in S, the agents in group S are still, Pareto improving. All of them are still at least weakly better off, and 1 of them strictly better off. Right? They've gone from having nothing to having 1 good each. So that's why this allocation fails the group fairness up to 1 good after version. And there's also a before version, and what this just says is that we want to remove the goods 1 per player in T before we do the reallocation. Right? So to see why this allocation fails that condition, think about removing 1 good from each of these agents in T, then reallocating the remaining square goods amongst S. We can still make the circle agent just as happy, they still get nothing, and the square agent much happier, they get 2. We might try and remove these 1 good per agent in T in a different way, maybe a circle and a square. In that case, we can reallocate like this. Still, it's the case that both agents in S are better off. Yep.
So in this example, the agents in S started with nothing?
In this example, the agent in S started with nothing, yeah.
If they started with
referring to adding these to the goods they already have, or would you take those away?
We would take those away. Yeah, they have to be able to improve, take T's goods instead of their own and improve. All right, so, okay. So how can we achieve these properties? I'm not going to show it here, but these properties are actually strictly stronger than some of the things we've discussed, like EF1. Okay, so how can we achieve them? One thing that we can do is we can actually take any locally Nash optimal allocation. So a locally Nash optimal allocation is one where it's rather obviously the local optima of this this Nash welfare function. It's where the product of utilities cannot be improved by switching a single good. Right, so the product of utilities VI times Vj Aj is bigger than it would be if we transferred a good G from J to I. And it turns out actually that its local Nash optimality is enough to guarantee both of our group fairness relaxations. What this also implies is that actually to guarantee EF1 in the freeness up to one good, local Nash optimality is enough. We don't need the full power of max Nash welfare in the global sense. Right, we can compute it in pseudo polynomial time by a local search algorithm. What we don't know is whether we can compute it in polynomial time. Right, so we don't know if we can compute a locally Nash optimal allocation in polynomial time. An easier question to resolve positively would be, can we even compute a GF1A and or GF1B allocation in polynomial time? Okay, I want to append to this discussion kind of another thought that we've had but have never written down, which is to think about known groups. So kind of what we had there in the discussion we've just had is we wanted to provide guarantees to all subsets of agents. When we want that, the best we can do is these up to one good per agent style guarantees. So just to illustrate that, suppose we have 6 identical players and we have just 3 goods that they all want. Right, the most fair thing we can do is just give one of these goods to each of 3 players. But then, if we want to guarantee fairness to all subsets of agents, we can kind of ex post define a subset S and a subset T, where S gets nothing and T gets everything. Right, so to kind of remove this unfairness, we have to take away all of these. We have to think about removing all 3 of these goods, right, to remedy this unfairness between S and T. What if we knew S and T in advance? If we knew that this was S and this was T, we would have done something like this. Right? We have these 3 goods to allocate. We'd give 1 to someone in S and 2 to someone in T. So we can ask a question, or we can define a property that I'll call fixed group fair up to one good, which says fix a partition of the agents. So we know the groups in advance. Is it now possible that there exists only a single good that we can take away from the entire group T, right? Not one good per agent, but a single good from the entire group, such that once we take away that single group, when we reallocate it amongst our group, amongst the other group S, players in S can't be strictly better off. Right? It's basically the same criterion as before, except now we know the groups, and I want to take away fewer goods. And you can modify this to get the after version, or even up to any good versions. So an open problem here, other than defining a better name for this property, is whether there always exist allocations satisfying it. Okay, so that was the group fairness part. And now we're going to move on from discussing relaxations of fairness, or kind of indivisible relaxations of fairness, to some other related topics, but a little more of a grab bag. So the first thing that I want to discuss is Nash welfare approximation. So we saw before that, or we've seen throughout this whole tutorial, that the max Nash welfare algorithm satisfies lots of really nice properties. It's GF1A/B, which implies EF1 as well as Pareto optimal. It's scale free, meaning that it doesn't matter what units the agents measure their utilities in, and it's a very natural kind of fairness efficiency trade-off. But like I mentioned before, it's NP hard to optimize, and indeed it's even APX hard. So in particular, approximating to within a factor of 1.00008 is NP hard. Okay, but can we approximate to some other constant factor? Well, shown by Cole and Katselis in 2015 that there exists a polynomial time algorithm that approximates the MNW objective to within a constant multiplicative factor of, actually the first paper was something like 2.88, and that analysis has since been tightened to give a constant multiplicative factor of 2. Right. Then there was some follow-up work, a Barman et al. Paper, which showed that there exists a polynomial time algorithm that gets you a constant factor of 1.45. This is actually almost the same algorithm as the one that gives us EF1 plus PO in pseudo polynomial time. You can actually just stop it a little early and it runs in polynomial time and still gives you this nice factor. So an obvious open question here is, can we close this gap? There's still a reasonable gap between the lower and upper bounds. All right. One other note on this Nash welfare approximation business. It's worth noting that approximate max Nash welfare solutions generally aren't going to retain the nice properties of the exact solution. Right? So the exact solution is EF1, it's PO. Approximate solutions may not keep these properties. But there are some approximation schemes which do keep some of the guarantees. So a recent paper by Garg and McLaughlin has shown that there exists a polynomial time algorithm that approximates the MNW objective to within a factor of 2, as well as keeping prop 1, keeping PO, and keeping 1 over 2n MMS approximation. And of course, along this line as well, you can recall that before we had a partial allocation that satisfied EFX and was also a 2 approximation to the MNW objective. I haven't got an explicitly listed open problem here, but there's kind of lots of directions in this space of how can we approximate MNW and keep some of the properties. I believe these two statements are the only two results along that line. Okay, next let's talk briefly about the price of fairness. So Nisag defined this earlier for the cake cutting setting. What about the indivisible goods setting? So just to remind you, the price of fairness is about asking what effect does requiring a fairness property have on the social welfare, being the sum of utilities. Okay, so the price of fairness is defined as the ratio of the maximum possible social welfare and the maximum social welfare of an allocation that satisfies our property P. Very recently, there's been actually another paper which defines a new notion called the strong price of fairness. And the strong price of fairness says what's the ratio between the maximum possible social welfare and the minimum social welfare of an allocation that satisfies P. Okay, so this feels a lot like price of stability versus price of anarchy. What's the best Nash equilibrium? What's the worst? This is, what's the best social welfare of an allocation satisfying P? What's the worst? Okay, so we can contrast some of these price of fairness results to the equivalent results in cake cutting. So it turns out that for indivisible goods, rather unsurprisingly, the price of fairness is generally worse than the price of fairness for cake cutting. That's just because fairness is a harder property to achieve when you have indivisible goods. So for proportionality, we get theta of n rather than theta of root n. For equitability, we get infinity rather than theta of n. Okay, you can also think about these other properties. So these are properties from a very recent paper. The difference between these style of properties and these ones is that this original paper by Karayanis et al. Considered properties that couldn't be guaranteed. Right? So there are instances where you can't be proportional or envy-free or equitable in the indivisible case. And what they did is they simply threw away those instances. Right? So they took the ratio over instances where you could guarantee these properties. This paper, on the other hand, doesn't take that approach, and they look at properties only that you can guarantee. So things like EF1, or what's the price of running the round-robin mechanism? What's the price of Pareto optimality? And they got results for price and strong price of fairness. So you could think about things like the strong price of fairness for these properties. That hasn't been considered before. All right. So far, we've been discussing all of this without any notion of strategy proofness, assuming that agents give their true valuations. What happens if we add strategy proofness? Okay, so nothing we've considered so far as strategy proof. Recall that in the divisible goods setting, we actually had a fairly rich structure of strategy proof mechanisms. Right? We had the 1/e approximation to the CEI utilities. We had the application of proper scoring rules. So we could certainly do at least some things. What can we do in the indivisible goods setting? And just as an example of how strategy proofness affects things, suppose you have an example like this and you're running the max-Nash welfare algorithm. Well, max-Nash welfare will give G1 to A1 and give G3 to A2, but it will give G2 to whoever reports the highest out of X and Y. So there's pretty clear incentives just to blow up your valuations. All right, so I'm going to work towards a characterization of strategy proof mechanisms for n equals 2. And they're going to be called picking exchange mechanisms. It's going to be a combination of picking mechanisms and exchange mechanisms. So let me start by defining what a picking mechanism is. What a picking mechanism is it first partitions the set of goods into two subsets, N1 and N2. Then what it does is it gives agent 1 a subset of offers. So it gives agent 1 a set of offers O1, which is basically a set of subsets of N1, and agent 1 chooses which of these subsets they prefer the most. Everything else in N1 goes to agent 2. Then we do the reverse for agent 2 and set N2. This is much more clear with an example. Suppose we have 6 goods. We'll define N1 to be G1 through G4 and N2 to be G5 through G6. What we'll do is we'll offer agent 1, out of these first 4 goods, would you rather receive G1 and G2, G2 and G3, or G4? And agent 1 looks at the evaluation function and says, well, the best, actually G2 and G3 is worth 10, G4 is worth 10 as well. Suppose we break the tie in favor of G2 and G3. So agent 1 chooses those, and the rest of these goods from set N1 go to agent 2. Then we do the same thing with agent 2 and the set N2 and the offers they received. Would you, as agent 2, rather receive G5 or G6? Agent 2 says they'd rather receive good 5, and good 6 goes to agent 1. And this is pretty clearly strategy proof, because there's just not that much for the agents to do. If these set of offers are pre-specified, if you're agent 1, why wouldn't you just choose the best offer you can? Agent 2 is going to make their choice independently, should take as much utility as you can get. So that's a picking mechanism. An exchange mechanism, again, partitions the set of items into 2. Now we'll call them E1 and E2. And what it does is, by default, it gives agent 1 subset E1 and agent 2 subset E2. But then what it also does is it offers a set of pre-specified exchanges. It says, would you both like to swap set S1, which is a subset of E1, with set T1, which is a subset of E2? And if both agents agree to the exchange, it makes the exchange. So here's an example, right? Suppose E1 is G1, G2, G3, and E2 is G4, G5. By default, we're making this allocation. Now we also have this potential exchange deal, which says, would you both like to swap G2 and G3 for G4? And agent 1 looks at this and says, yes, G4 is worth 7, G2 and G3 together are only worth 5, I'd like to swap. Agent 2 says G2 and G3 are worth 7, G4 is only worth 4. They both want the swap, so we go ahead and make it. That's an exchange mechanism. And then a picking exchange mechanism is, at least up to some tie-breaking technicalities, simply to run a picking, simply to partition our goods into 4 sets, N1, N2, E1, E2. We run a picking mechanism on N1 union N2 and an exchange on E1 union E2. Okay, so what they show is that for n equals 2, an allocation mechanism that always outputs a complete allocation is strategy proof if and only if it's a picking exchange mechanism. So this is a really nice characterization to have, and it lets us say a lot of things about the power of strategy proof mechanisms, at least in this n equals 2 case. So we can say lots of things as a corollary of this result. One is that any strategy proof mechanism that allocates all goods cannot achieve any positive approximation of the minimum envy or best proportionality guarantee. And by that, what I don't mean is this fundamental impossibility that comes from having indivisible goods. I mean this relative to the best thing that an indivisible good allocation mechanism could do. As long as m is at least 5 and n equals 2, no strategy proof mechanism that allocates all items can be EF1. And we can also get a bound on the MMS approximation, 1 over the floor of m over 2. That's the best we can do. And actually it turns out from a result from a previous paper that this is a tight bound. Okay, so this is really nice. It gives us a pretty complete picture of what we can do with strategy-proof allocation mechanisms. What it doesn't really do is give us a picture of what more general strategy-proof mechanisms look like. So what about if it's not the case that all goods have to be allocated? This was kind of quite powerful in the divisible case. Right? We had that approximation algorithm that first computed CEI allocations and then dialed them back. Right? We can't do that sort of thing here. Another one is what about how these strategy-proof mechanisms look for n greater than 2? So Manatidis et al. In their paper, they they gave some class of strategy-proof mechanisms, but there's no sense in which this is or should be the complete class. Okay, now let's move on to talking about allocating bads. So bads, as they were before, are going to be items where our valuation function now maps into non-positive numbers. Okay, so it's often the case that techniques and analyses that we use for goods don't carry over to this setting. Sometimes they do with modification, sometimes they just don't seem to work. And we really don't know much about the bad setting. So all I can give you is kind of a smattering of just a few results. One is that if we think about MMS allocations for bads, we can get a 2 MMS allocation, and actually it's been improved to a 4/3 MMS allocation. This approximation factor has gone from being less than 1 before to more than 1 now, and that's just because in the bad setting, the approximation is you get an allocation that's more bad than your MMS share, not less good. Okay, so there's no sense in which this bound is tight. Could certainly potentially be tightened. A more general model is one where we're allocating both goods and bads. Right, so now we're mapping subsets just into real numbers. And here we have a setting where items can be goods for some agents and bads for others. Right, so it's more general than just goods or just bads. So one thing we have to take care of is we have to slightly generalize some of our definitions. So now when allocation is envy-free up to 1 item, if for all players I and j, there exists an item g in the union of aj and ai, such that when we remove it, we remove the envy. So we'll remove it from agent i's bundle if it's a chore or a bad, or remove it from agent j's bundle if it's a good. And you can generalize other properties like prop1 in the same way. Okay, so what can you do here? Well, one thing that you can do is you can still compute an EF1 allocation. It's already somewhat more non-trivial than computing an EF1 allocation just for goods or just for bads. So how it works is they run a double round-robin algorithm. They first allocate all the items that everyone agrees unanimously are bads. Right? They do that by round-robin. And then, in the reverse round-robin order, they allocate all the remaining items, items that at least someone thinks are goods. Turns out that this satisfies this more general version of EF1. They also show for n equals 2 that you can get an EF1 plus PO allocation in polynomial time always. So as I said, there are a lot of things we still don't know here, and here are just a few of them. We don't know if an EF1 plus PO allocation always exists for bads. So we have a lot we can bring to bear on this problem in the good setting. For one, max Nash welfare. Well, it's not clear at all how max Nash welfare should be generalized for bads. We have things like kind of market competitive equilibrium techniques. Again, it's not clear how they generalize to bads. An easier existence question is prop1 plus PO. Can we even get that? And of course, EFX. We don't even know that for goods. We certainly don't know it for bads. Okay, what have we not covered in this section? We haven't covered a property called envy freeness up to 1 less preferred item, or EFL. So this is kind of an interesting definition. It's a definition it's a property that is stronger than EF1, and it's still guaranteed to exist. And you can look up the definition in this paper here. The existence of EFL plus PO allocations is still an open question. We also haven't looked into various other constraints that you could place on these problems, right? Like you could have a social network structure on the agents and think about having agents compare themselves to only their neighbors or something like that. You could also think about connectivity constraints on the items, right? What about if the items lie on a graph and you want to allocate agents only connected bundles? There's also work in things like asymptotic results. Can you guarantee these properties as number of agents or items gets large? Or how often can you guarantee these properties? Okay, and many others, including from the papers we've presented, of course. Okay, so now let's just move on to a couple of extra topics. So these are topics which are definitely still in the fair division realm, but slightly outside of the model we've just presented. One such topic is Leontief preferences. So Leontief preferences, we have a set of resources M, and our agents are going to require these resources in a certain ratio, di. And so this is things like if you have tasks to complete, maybe with computational resources, and you need some ratio of CPU to RAM to complete a task. Right? You need both. One on its own is no good. And again, our allocations will be fractional, or not again. Allocations here are going to be fractional. So Aij is going to denote the fraction of resource j that agent I receives. So Leontief preferences are essentially the number of complete sets of resources that I receives. So here's the formal definition. It's the maximum possible y such that the allocation for every resource is greater than y times the demand. So here's an example. Like I said before, you might have two types of resources, CPU and RAM, and an agent might have tasks that require 2 units of CPU for every unit of RAM. So the demand vector would be 2, 1. Now if they receive 3 units of CPU and 3 units of RAM, this is the extra RAM is no good to them. Right? They need these in the ratio 2 to 1. Okay, so there's been kind of a very pervasive algorithm in this setting called dominant resource fairness, which was first proposed in 2011. So what it does is it defines the dominant resource for agent I to be the resource that they demand the most of. Right? And then what it does is it simply equalizes the allocation that each agent receives of their dominant resource. So it kind of runs MaxMin on the dominant resources. And this is a really nice algorithm for this setting. It satisfies basically everything we could want it to satisfy: proportionality, strategy proofness, NV freeness, and Pareto optimality. So let me just give you a visual demonstration of how this works. So suppose we have 3 resources that's represented by these 3 bars, and every agent has some demand vector. So this agent demands 0.2 of the first resource to 0.1 of the second to 0.3 of the third. And what we're going to do is we're going to think about filling the allocation of these agents in the ratio they demand until we run out of resources for at least one of our goods. So hopefully this animation is somewhat clear. Okay, so you can see that the dominant resource for agent 1 is the middle resource, for agent 2 is the last resource, and for agent 3 is the middle resource. And the heights of those dominant resource bars are equal. And we've filled up the allocations in proportion until we've run out of one of the resources. All right, so that's just kind of a very brief look at the main result in the space of Leontief preferences. Let's also talk a little about ordinal preferences. So ordinal preferences are preferences where we only extract ordinal data, ordinal preferences, rather than cardinal information or numerical information. So instead of valuation functions, we're going to take in these preference orderings over items. So here, for instance, agent I says that they prefer good G2 to G3 to G1 to G4. And we're going to assign agents, again, fractions of each item. Okay, so an allocation will just be a sum over Aij Gj, where Aij is the fraction of good J that agent I receives. And in this setting, we tend to interpret these more as we tend to interpret these as lotteries over integral allocations, and that's just for traditional reasons where these ordinal mechanisms tend to be used for things like matching problems, allocating housing or classrooms or things like that.
Are numbers known?
Sorry?
This are they known?
Where the goods are known, these are just the items.
Yeah, but what's in the sum? What is
Oh, the sum. Oh, this
fraction?
A is Aij is the fraction of good j that agent I receives. So this is just a way to denote the allocation. It's not clear that sum is necessarily the best thing. Yeah. Yeah. No. I'll get. Yes. Yeah. There's no notion of utilities here. Just ordinal preferences, right? You can, we're told that agent I prefers G3 to G1, but that's all we know.
What kind of preferences do they have for the value?
Good. So that's the very next slide. So we now define preferences, or at least partial preferences, over these bundles, over these lotteries, by the stochastic dominance extension. Right? There are others that we could use. Here we're going to focus on this one. So what this says is that agent I prefers an allocation A to an allocation B under the SD extension. If and only if, let me kind of define this recursively. What this says is that allocation A should give agent I more of her most preferred good than allocation B does. It should also give her more of her 2 most preferred goods than allocation B does, and more of her 3 most preferred goods. For all k, allocation A should give agent I more of her k most preferred goods than allocation B does. Right, so this is a sense in which A would pretty clearly be better than B. You can think of many other extensions, right? These are just a few. There are probably more out there. You could probably define more unknown ones. And you can look those up if you're interested. You can also think about eliciting ordinal information directly over entire subsets, right? So not bothering with these extensions and just eliciting this combinatorial information, and then you get into computational and elicitation problems, and there's a whole literature on that, including this paper, but also others. We're not going to consider that setting here. So what can you do in the setting that we've defined? Well, there are a couple things that you can think of doing. One is you can run random priority. And what random priority does is it fixes an ordering of the agents, and then agents select their favorite m over n goods that remain. Right, so if there are 5 agents and 10 goods, we fix an ordering of the agents, then they each come and they select 2 goods, one at a time. Another thing we could do is an algorithm called probabilistic serial. So how this works is we're going to think of agents eating the goods at some constant rate equal across agents. So at any time, what agents will do is they're going to consume their most preferred good that is not already completely consumed. And then any good that they've consumed, that they've eaten, is going to be in their allocation. So this is easier to see with an example. So suppose we have these 2 agents. Agent 1 has this preference, agent 2 has this preference. Right, what will random priority do here? Well, one ordering is agent 1, then agent 2. So in that ordering, agent 1 will come, and they'll choose their 2 most preferred goods. That's G1 and G2. And agent 2 will get G3 and G4. If we flip the ordering and agent 2 comes first, then agent 2 will choose G2 and G3. And agent 1 will get the remaining 2 goods, G1 and G4. So let's think about what the agents receive in expectation over these orderings. Well, no matter what, agent 1 was going to get good 1, because they select it in their as one of their first choice 2 items, and agent 2 doesn't. So agent 1 gets good 2 no matter what. Likewise, agent 2 gets good 3 no matter what. Goods 2 and 4 end up being split. What about probabilistic serial? Well, it's actually pretty easy to see what that will do here. As soon as time starts, agent 1 starts eating good 1, and agent 2 starts eating good 2. And they eat at the same rate, so at some time, after some time, agent 1 has completely consumed good 1, agent 2 has completely consumed good 2. So they get those. Then, both of those are gone, so they both start eating on good 3. right? There's good 3, and for agent 2, there's good 3, right? That's out of good 3 and good 4, they both prefer good 3. Delete that at the same rate, so each of them will get half of good 3, then they move on to good 4, and they each get half of that. All right, so those are two possible mechanisms. What sort of properties might we want them to satisfy? Well, one is SD efficiency, and this is really just Pareto optimality extended to these stochastic dominance relations. Right, so it says there should not exist any alternative allocation that all agents weakly prefer and some agents strictly prefers under the SD preference extension. And Bogomolnar and Moulin showed in 2001 that a probabilistic serial satisfies SD efficiency. In contrast, random priority does not. So what we get here is no matter who goes first, agent 1 would choose good 1 and good 2, and agent 2 would choose good 1 and good 2. And then the other agent would get left with G3 and G4. So allocation is going to be a completely uniform allocation over these goods. However, both of these agents would prefer... Oh, that's a bug. Both of these agents would prefer, actually, if agent 1 got all of good 1 and agent 2 got all of good 2. Right? Agent 1 prefers good 1, agent 2 prefers good 2. So they'd like to make that swap. Likewise with good 3 and good 4. Agent 1 would like to take good 3, agent 2 would like to take good 4. So this is not an efficient allocation. Right, what else might we want? We might want SD strategy proofness. This is just strategy proofness extended to this stochastic dominance relation. No agent should be able to improve their allocation under these SD preferences by misreporting their preferences. Okay, and here it's easy to see that random priority is SD strategy proof. And that's because if you have some ordering of the agents, when it's your turn to come and take your favorite M over N goods, why wouldn't you take anything but your best? You're not going to reappear in this ordering, so just take the best goods you can while you're here. You're not going to come back. On the other hand, probabilistic serial is not SD strategy proof. All right, here's an example. I don't think I need to work this in detail. The intuition here is that it might pay to be strategic about which goods you eat. Because if I know that you don't really want to eat my favorite good, and you're going to leave that till later, I might want to also leave it, eat some good that you do want, and then come back to my favorite good later before you get to it. All right, so we have one mechanism that satisfies one of these properties. Well, we have two mechanisms. Each of them satisfy one of these properties. It's perhaps not surprising that there's actually an impossibility. Subject to this equal treatment of equals condition, which is like a weak condition saying you shouldn't favor some agents over others, you can't get SD efficiency and SD strategy proofness together. Maybe a brief note that one thing that you can get in combination with at least SD efficiency is you can get MV freeness as well. This probabilistic serial mechanism is not only efficient but also envy free. Right, I'm not going to kind of show you why that is, but the intuition is that why would I envy what you have? I could have been eating what you were eating anyway. All right, so the very last part is about public decisions, and Nisag's going to present this part.